Today, we're excited to have Dr. Sarah Wise with us. Sarah is an associate professor in agent-based modelling at the Centre for Advanced Spatial Analysis of University College London. She completed a PhD in the Computational Social Science Department of George Mason University and has been involved in many interesting research projects around people, infrastructure, social network analysis, and much more. Today, Sarah is here to talk to us about the use of agent-based modelling in exploring novel urban parcel delivery systems. Thank you very much, Sarah, for being here, and I'll hand over to you.
Thanks so much for a lovely introduction. And again, thanks for having me at this. Onto the actual content of the talk. As Thomas mentioned, I am a lecturer, or now an associate professor in agent-based modeling specifically, and I apply that to a number of different topics. In this talk, I'm going to be talking about specifically my work and the work of at least one other person in terms of applying agent-based modeling specifically to the last mile delivery of parcels. The context in which this works, we used to use this slide before lockdown happened, and the importance of delivery was quite as obvious. But even as early as 2016, it was very clear that the increase in demand for parcel delivery had been going up and up. You had stranger, sort of more exotic new things that needed to happen, like less than van loads, where people wanted things delivered on the same day. Product returns were a larger and increasing issue. Delivery failures were a larger and increasing issue. There were a lot of concerns from the part of the industry. It was very competitive. It was very easy to enter, which meant that the cost per parcel actually delivered ended up going down. So the economies of scale were sort of an interesting thing and were very spatially determined. There was a real need that was perceived by a number of project partners for this investment in the infrastructure and in the planning that was going to support this kind of thing. There was a real observed worsening in road conditions, both the physical condition of the roads and also congestion, and the consequent knock-on effects for delivery. Parking is an increasing issue and something which is decidedly unsexy, difficult to gain anyone's excitement and interest in at a sort of municipal level. There's a lack of affordable land in terms of companies wanting to create depots within urban areas, but there are arguments for that being quite powerful. And there's a lot of pressure, again, at both the national and the local level to decrease emissions that are associated with CO2 and other greenhouse gases. Those are all things which require more of a sort of a larger scale view of the situation that's happening. And that's something that we think is particularly compelling, a particularly interesting thing that we can look at using novel kinds of simulation. So in particular, in this talk, I'm going to present two examples of agent-based modeling for last mile delivery. I'm going to sort of talk about the workings of the ABM and how they allow us to capture some interesting things. I'm going to very briefly present the kinds of results and insights that we can derive from these methods, which I think are arguably very have the ability to speak to our sort of end users and our companions in other parts of the stakeholder environment in ways that I think are interesting. So the first project is going to come from some work that I did with the Freight Traffic Control 2050 project. This was a consortium among a number of universities, Southampton, Westminster. Someone ended up in Liverpool, which made us 5. Obviously, UCL was me, and then Lancaster. So the idea of the project was we wanted to help a series of project partners in the industry side understand how their freight carrying worked at sort of a systematic level. So not just at the level of the individual deliveries, but how as a fleet, they were able to look at sort of different approaches to last mile, different sort of uses of data to understand what they were doing and to understand how they could do it better. So we were trying to recreate, to a certain extent, with the agent-based model, some of the data that we were getting in. We wanted to be able to create these same patterns synthetically to make sure that we understood what was actually going on in the first place. So they gave us a lot of data that was very beautiful, and it looked like this, and we were very excited. I mean this sincerely. Where we had tracks of where, for example, vans were going, what they were doing, when they were getting there, this kind of thing. And we were able to extract this, and I should clarify, my project partners were the ones who did this, and they did a brilliant job. they were able to aggregate this into a bunch of information, which was actually things that our project partners had never looked at in their data. So they found a couple of things that they really hadn't expected to find. So for example, on average, the amount of the time that a van is outside of a depot, it spends 62% of that time parked. That is to say, 62% of the time that the van is not in the depot being loaded or being serviced or being whatever else, it is stationary, which was interesting because they then took that on to their insurance people and said, we're only driving like 38% of the time. And they actually got a discount in rates. So that was fun for them. But you also had something where the van drivers were going out and they were walking per round a minimum of 4.5 kilometers. So you had some people who were walking as much as 12 kilometers on an 8-hour round. So the idea was, they're not supposed to be spending, on average, as you can see, it's around 7 hours, but you were getting people who were walking something like 12 kilometers in a day, which was a lot more than they expected. And that had implications for the timing, which they had not been able to factor in because they weren't thinking about van driver walking. They were also noting that the number of parking stops, they said within a particular round, there was one driver who stopped their van 72 times. They parked their van 72 times in approximately 8 hours, a little less probably. So these were dynamics and these were trends and these were aspects of the system which they hadn't really sat down and looked at and thought about and talked about. And these were some of the things that we wanted to be able to recreate with our simulation because we knew that if we were able to get these kinds of numbers, that would mean that our approximation of how the individuals were behaving had some realism. If we could reproduce this at the fleet level, but also at the individual level, we could be more confident that our model was capturing these dynamics and therefore we could tweak aspects of the environment and see what impact that would have at a fleet level. We also had this really great spatial data. So one thing I want to show here as an example of the round. So the white trace here is where the GPS tracker actually shows that the driver was. You're also going to see some yellow and red lines. The red lines connect the parking spaces of the vehicle. So that's the vehicle was moved from here to here to here to here. The yellow lines will connect the parcel where it was delivered to where the van stops. So you can see where they're walking from any given parking space. So you can see things, for example, like they've actually walked all the way to here from their parking spot here, which was very interesting to us and not at all the expectation. And trying to understand why things like that would happen, inefficiencies that we sort of perceive in the data was a really important part of this conversation and this ongoing relationship with our industry partners. If you're curious, it turns out that timed deliveries have a huge impact on the way that people do deliveries. So they're subject to constraints in terms of a particular parcel has to be delivered by 10. So they'll just go and deliver that first thing, even though that's not the most efficient way for walking. So that has, again, consequences for walking distance, the timing on everything else, and so forth. So we were trying to create these individual patterns, these individual sort of relationships between parking spaces and locations within the system. We were also trying to recreate at the system level what the fleet level of this looked like. So this is a simulation. We have data from 2 different industry partners here. One thing to note, the yellow is from a depot which is very far outside the city. So there's maybe 7 miles of stem mileage. So they'll drive 7 miles before they get to about here. And then all of their vans, there's maybe 12 of their vans, are delivering in the same area. So you'll have 12 vans drive 7 miles each, and then all within this fairly small part of London, if you're familiar with this part of London. The green and the blue vans are all from the same company. They're from different depots on either side of the river, but they're all in the same company. And this is just a pure GPS trace from them. One of the things that I wanted to use to communicate with them about this was that we had said to them, we suspect that we could help you partition space into some more reasonable areas where you could make deliveries, where there's not a lot of overlap, where you're not parking in spaces that your own employees want to park in. And they said, no, we're very efficient. And we said, yeah, but I think you could probably optimize things. And we showed them this video and they said, yeah, okay. I mean, it's possible there's a bit of overlap in the areas that we're serving. So, you know, the degree to which you had overlap between the same drivers, between the same companies, you know, internally was more than they expected. So in terms of sort of selling this to the van drivers or to other members of the company, that kind of visualization was quite useful. So we were, in a sense, trying to recreate aspects of those dynamics that you're seeing. We wanted our individual traces to match, and we also wanted the fleet level to match. So what we ended up doing was we went in and we created an agent-based model. I'm just as a point of curiosity, I think everyone can use a little emoji thing to say, what is the familiarity of this group with agent-based modeling? Are people broadly comfortable with it as a concept? All right, I have one thumbs up. Okay, so just to very briefly then go over what this typically means. An agent-based model is a model where you break up the system into the agents, these little active individuals who have information, who have behaviors that they do. So in this example, for example, we say, all right, there's a number of drivers. There are people who drive around the space and they make deliveries. There's a number of vehicles. These are the things that the drivers move around the space and they contain the parcels. There are these individual little parcel units. So we create a bunch of parcels and say where they should go. And we have a depot, which is the place that the parcels are created. So the depot creates the parcels, which are then their own little things. The driver will go to the depot and they can have a bunch of parcels and then they'll put them in their vehicle. They'll put all the parcels in the vehicle and then they'll drive the vehicle around and they deliver things to where it needs to go, right? So this was a useful way to look at things because we could therefore change things like, what if you move the location of the depot to somewhere else? What if you create a smaller depot within the city limits? What if you create a series of depots? What if you change the nature of the vehicle, which is something we'll come back to? You know, what are the different ways that we might use these different elements, combine them in different ways in order to understand how this system works, right? It's all very well and good to say how something works right now, but if you anticipate a huge increase in the number of parcels that need to be delivered, you might want to have a system which can capture how, as that changes, the behavior of the drivers. So the model itself then, the behavior of the driver is very simple. As long as they're at the depot, they'll get around. If there's nothing to be delivered, they'll finish. If there is a round available, they'll take on a new round. They'll cluster the parcels that need to be delivered into a series of parking spots, so the areas that, you know, from which they can be served. And as long as they are not finished with the round, as long as they have more parcels still to deliver, they'll drive to the next parking space. And as long as there are parcels which can be delivered from that parking space, they'll deliver the next parcel. So there's a bit of modularity on things that you can change in terms of how you cluster the parking spots, how you select parking spots, how you associate the parcels with a given parking spot, and the time around it. So those are things that we've intentionally kept quite modular. But the gist of it allows us to say, okay, so, you know, with different resourcings of the number of drivers, different resourcings of the kinds of vehicles and their locations, how can this work? Just in the interests of sort of moving this along, the simulation that we created shows a part of East London that we were interested in simulating. What you have here is the sort of nice, I guess I'll call them lavender spots. Those are actually vans, which contain a number of parcels, and the beautiful little pink friends, those are the drivers themselves. So the drivers operate separately from the vehicle. And the colored spots are parcels that are being delivered. So just to establish, all of these parcels are synthetically generated, so we're not revealing any super secret data about where people are doing deliveries. So as you can see, they are either driving around the space, they might be walking to the vehicle, they might be walking to the delivery. So you can track these individual drivers as they do various things. Their speed outside of the van and their speed inside the van are obviously different. But so you can kind of come to understand a little bit more about how they make these deliveries at a fleet-wide level. In this case, I've simulated them with having non-overlapping areas for delivery. So they each have a nice little cluster, which is separate from everyone else's cluster, so they won't be parking in each other's spaces. There's a lot to be said in terms of the way that you partition rounds. That is, you say, one person is going to deliver all of these parcels, which I think is really potentially quite exciting. And I would love if someone picked up our code and did that. Do let me know if you're looking to do that. But anyway, so sort of moving on, we end with this understanding of where all of these deliveries have been made, what the timing on that is. We have a certain range of failed delivery. We have a failed delivery rate, so we're able to estimate things like that as well. And we're able to sort of simulate how much walking they've done, how much driving they've done, how much of the time the vehicle spent parked, all that good stuff. Yes, thank you. So then we're able to, sort of go back and compare the real and the simulated data. So we can say, all right, well, our simulated vehicles are parked for probably as long as they should be. It's totally generated data for the delivery location, so that might be part of it. And our drivers tend to, the rounds are not as optimized as they could be. So this is a sort of an early work kind of a set of things, but you're able to compare quite directly the walking distance, the number of items delivered, the driving distance within the area, and so forth, and to compare that with things like stem mileage. That also means that we can compare a simulation of, let's say, all van drivers with a simulation of what if we replaced two of the vans with porters, which is to say individuals who don't have a van, they are carrying things in a bag and they're making deliveries with the bag. This is something which we were actually starting to see in London before the lockdown. So you would see guys with very large, effectively the kind of bag that you would have your football kit in, over their shoulders carrying parcels around. That's very achievable for quite a lot of the sort of sizes of parcels that the people that we're serving were interested in. So you can absolutely take quite a lot of the load off of the vans in that sense. So we were interested in sort of saying, okay, well, what percentage of the time is someone going to be parked if quite a lot of the work has been taken off by these guys who are sort of walking around? How much is driven, how much is walked, and so on and so forth. So we wanted to sort of look at then how you could compare, how you could change aspects of the fleet and turn that into sort of different levels of delivery. We're able to talk about that in that sort of everyone's favorite statistical table of comparing things. We're also able to visualize things like that. So where does the driver walk? Where does the vehicle go? How long are vehicles stopping or spending in various areas? Van parking is a surprisingly contentious issue if you are in the right circles. And there are experienced drivers know where they can park in order to take advantage of lax enforcement on parking regulations, which is extremely important to their round duration. It makes a big difference. So understanding where vehicles sort of might optimally be stopping and understanding how that intersects with the city's goals in terms of promoting or discouraging light good vehicles moving around is something which is perhaps worth showing, and we're able to visualize that in a fairly direct way. So these are things that I think we can turn into insights which are digestible by our project partners, digestible by our industry partners. We can render it in terminology which is accessible to them, and I think that's very important. Some of the things that we are at some point hoping to do, I have technically moved on to another project, but I would love if someone else wanted to pick this up. The code is all available on the GitHub that I have included below here. But we would love to do a sort of comparison of small central depots versus larger suburban depots. You get a lot of stem mileage, which is just driving in light good vehicles, which you could absolutely sort of play around with in interesting ways. Alternative modes of transit, such as cargo cycles, hold that thought. Whether there are ways that you could encourage different industry partners to agglomerate or share spaces within the city in terms of their depots, or looking at things like policy changes such as the low emission zone or the ultra low emission zone, I believe we're calling it now. So there's a lot of stuff that you could theoretically experiment with here, and I think it could be profitable. One thing that one of my students, not this year, but last year did, I had a student who was particularly interested in looking at cargo cycles. So he did a collaboration with a cargo cycle delivery company based in London. They're called Tride. And Ahmed, who's a brilliant student and did very well in his dissertation, decided to simulate the way that the parking side of cargo cycles versus light good vehicles, how that might contribute to these kinds of questions. So light good vehicles are effectively what in the UK we seem to call the white van dynamic. So the large sort of van, there's a lot of parcels thrown on the back. They are not particularly well regulated. They're not particularly well tracked in the UK. Obviously, that's because in a lot of cases, they're private contractors. But within the city, there are many more light good vehicles within the inner boroughs and within the outer boroughs. They contribute significantly to congestion. They are terrible in terms of emissions, and they're actually pretty risky. Like the risks they pose to cyclists, they're involved in a disproportionate number of events. So light good vehicles are an interesting thing. And the question of sort of, is it possible to replace some of these with cargo cycles was interesting. So Ahmed was focusing on what we sort of jokingly called the last meter. So very literally from the place where you park to the place where you make the delivery. So he ended up simulating the space as a series of buildings. So for example, there's no building in this gray spot, but these other places are buildings which might demand deliveries. He had a curb which had legal or illegal spaces that you could park. And then he simulated in green little cycles, which is very clearly a biased coding to make them look friendlier. But I've declared our biases up front, so hopefully that's acceptable. There's the gray, which is the light good vehicles, the vans that are making their deliveries. And then there's additionally the rest of the traffic, which are these sort of orange spots. So in this case, as a sort of first pass, he was interested in looking at how the presence or absence of legal parking impacted the balance of power, as it were, between the utility of cargo cycles versus vans. So the idea is you would park at the closest available space, and then if you could make the delivery, you would do that. So you have the time cost associated with traveling from your curbside to your building side, and so forth, with the understanding that the parking process has impacts for traffic overall. Right, sorry, I forgot, I actually labeled them, but yeah, cargo cycles, vans, other vehicles. Again, a fairly straightforward behavioral chain, as long as the agents are in the space or are being told they should update. And if they're, not a building, they'll drive along the road if they can. If they need to park, they'll attempt to. If they can't park yet, they'll wait around, they won't move, and they'll wait to try to park. If on the other hand, they want to move forward, they will attempt to move down the road and so forth. So it's pretty simple, but you end up getting these fairly interesting insights in terms of how many parcels get delivered on what time frame by bicycles, by vans, what is the average speed of all the vehicles in the space, what does that mean for the free-flowing traffic of the non-delivery vehicles in this space. what are the implications for this system as a whole, rather than just from the perspective of the delivery vehicles themselves. So one of the things that he also visualized, which I quite enjoyed, is he was looking at what is the sort of level of capacity of the vans, how much could they theoretically be delivering versus how much are they actually delivering based on the restrictions, the restraints of the availability of parking, blocking each other out of parking. So, if you're different companies, or even more depressingly, the same company, which you can't park in because your mate's already in the spot, that has consequences for your efficiency. In terms of not being able to park because the traffic is too slow and someone has taken your space by the time you get there. So these were things which he was able to actually visualize and show that, the capacity is not everything. It's not actually all it's cracked up to be, because the effective capacity of vehicles, even in this circumstance where cycles are subject to a lot of restrictions that they aren't actually, vans really don't enjoy the advantage that we expected that they would. In terms of what he therefore identified, is he said that the availability of parking spaces is the thing that really influences van effectiveness. And it was interesting because I don't believe I've mentioned to him the inclinations of vans to park illegally in the real world, but he was able to recreate that. He said, in order to get these levels of successful deliveries that I'm seeing in reality, you would have to park illegally. And I said, how interesting. What an interesting finding. There are very limited circumstances in a dense inner city level of delivery density where a van could outperform a cargo cycle. It's really not, unless you're delivering something like a washing machine, realistically, you can largely rely on smaller goods, smaller forms of transit. Amit very kindly made all of this code also available on GitHub, which is lovely of him. So if you're interested in looking at it, his is all in Python, mine is in Java, sorry. But so his is probably friendlier, and it's on his GitHub, so you'd be very welcome to look at that. Another student of mine recently actually did a further piece of work looking also at electric bikes in the context of Hong Kong, but the piece of work has only just been marked today, which was also a distinction, just to clarify. So I was not allowed to present for work until later, so I apologize. But other pieces of work in terms of using an agent-based approach to understand this kind of last meter or last mile at a system level are ongoing. So I think that it's an open field of research, and I think it's potentially very interesting. So just in terms of what I wanted to sort of hope that you guys got from this talk is that we can look at a lot of different questions surrounding the last mile using this kind of approach. There are a lot of different kinds of outputs, so we can create a lot of different kinds of insight where we can take different aspects of the system, pull them out and study them at a bunch of different kinds of granularity, using a lot of different kinds of data to make sure that we're capturing the dynamics of the system at both the sort of high level, at the fleet level, but also at the level of the individual vehicle. That gives us confidence that we actually understand the system, and that gives us confidence that what we're saying about the fleet level behavior is actually something that can be usable by our industry partners. The kinds of questions that we ended up asking and the kinds of conversations we ended up having with drivers, we found did increase their buy-in in the process. The way that they sort of ended up thinking about things was very useful, both for us and I think ultimately for them. So as long as it's done respectfully, I think it can be a really great experience. I will say, I think code should always be made available in the open source context, because a lot of the dynamics I'm describing are very complicated. They feed back on, or rather, I should say, they're not complicated, they're complex. They feed back in on each other. As you saw, the behavioral frameworks there are fairly straightforward. You can get quite nuanced on how you cluster the rounds or how you cluster the parking spaces, or you can do real fancy route finding if you want to. But it doesn't actually need to be that complicated. You just have to be aware of what are the questions, what are the pieces of data, what are the pieces of context that these individuals are using to make their decisions, and what shapes their environment. So that can be difficult to communicate. So the availability of the code open source to show what you've actually done is incredibly important. So that's just my small soapbox, and I'll step down from it. And the work continues. I think it's a point of interesting research, and I hope people will take it forward as much as possible. That is, I believe, I'm almost to the end of my scheduled time, so I will attempt to finish maybe even 2 minutes early. Thanks very much for your attention. I'm very happy to answer any questions. And again, thanks for having me.